What did you get, Charlie Brown?
I got a rock. I got a rock. Rock. I got a rock. 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 I got a rock. I got a rock. I got a rock. Rock. Rock.
What did you get, Charlie Brown?
I got a rock. I got a rock. Rock. A rock. I got a rock. I got a rock. Got a rock.
What did you What did you get, Charlie Brown?
I got a rock. I got a rock. 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 I got a rock. I got a rock. Got a rock. Got a rock. 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 I got a rock. I got a rock. 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 I got a rock. I got a rock.
Alright, so today we're going to start on the next module, which is file input and output. And it won't take that long, maybe today and maybe Wednesday, depending on how much we get through. But the short of it is we're only going to focus on very simple input and output. Because if you are going to be doing file I/O in any capacity in real life, you're going to want to bring in a library to do it, right? The reason that we look at files to begin with is because files are stored in memory, usually on disk. But in reality, everything in the Unix world is a file. A file is a file. Directories are files, right? Programs are files, both when they're stored on disk, not running, but also when they are running and stored in memory. So anything stored in memory is basically a file. If you are communicating from computer to computer over a network, you are opening what's called a socket, or a connection between these two computers. On one end, to send data, you write to that file. On the other end, to read data, you read from that file. That socket, that connection, is a file. Buffers are files, right? So everything is a file. A file is a file. Again, usually files, we think of them as data stored on a disk. Let me check this really quick. Yep, that's okay. Anyway, they are. We usually think of them as being, physical, like files that are stored on a physical medium. You can read input, you can write output. So when we say that we're going to read from a file, we mean file input. When we're going to write to a file, that means that we're going to be doing file output. Right? Files can be plain text or binary files, as we've seen before. Like I tried to open up a compiled program, and it was just a bunch of garbage, right? In fact, it wouldn't even let me do it. Or they may be plain text where you can actually read it. They may be intended for humans or not, right? For example, this is not really intended for humans. This is not very readable. If you wanted to display this kind of data to a human, how would you do it? In a nicely formatted table with headers, right? Maybe rows, row after rows, and everything is nicely adjusted, etc. You don't have all the data running together and a bunch of commas everywhere, right? Well, how else might you store this data for a task called EDI, which is electronic data interchange? In other words, we want our data to have a universal format so that if I write a C program, I can read the data. If I write a Java program, I can read and write the data as well, right? We want an electronic data interchange format. If we store it on disk, send it over a network, we want other programs to be able to read that. And there are lots of formats for this: XML, JSON, or base64 encoding. Here's an example. There's the same data that I've converted over to XML format. Right? And you've seen this before in lab, I forget which one it was, or no, it's your upcoming lab, excuse me. You'll actually be writing output to an XML file tomorrow, right? And it's going to look something like this. Now, these are called elements. The Langle-Wrangle there, it denotes an element. And then elements have sub-elements. So this is the root, this is the row. Normally I would call this books, and then this one is going to be a single book, right? We can actually do that up here automatically, books and book with this tool, right? There we go. And that'll look a lot better, right? Here's all my books, and within that I've got one book, I've got two books, etc. Each one of these tags is called an opening tag. The closing tag behind it is the same thing, but with a / to close off that element. This indentation here is just prettifying it, making it look nice so that you can read it a little bit better. But otherwise it tells you what the title is, the first name, the last name, the year, the rating, etc. A little bit more compact way of doing that is, a more modern way of doing that is through JSON, JavaScript Object Notation. And even though it's called JavaScript Object Notation, it is a universal format at this point. Every language is going to have some library that read JavaScript Object Notation. And it looks kind of like this, right? It looks exactly like this, in fact. This square bracket denotes an array. Each element in that array is denoted with an opening and closing curly bracket. And then you have what are called key value pairs. So this is the key, the title, colon, and then there's the value of that thing. Here's the first name, colon, and then the value of that thing. Most things are going to be strings, and so they are all double quoted. Otherwise, for numbers, those are just literal numbers there, 2007 and 4.62. Yet another format is going to be base64 encoding. This is so that you can send binary data or just any old data. In this case, I converted this data over to this string right here. It's base64 encoding. In other words, it's not binary, right? It's not 0, 1s. Instead, it is base64. It's not even base 10, 0 through 9. We have 64 symbols to denote all the symbols in our counting of base64. That's going to be 0 through 9, that's 10. A through Z, both uppercase and lowercase. Count with me, that's 62, right, total. And then what else do we have? I think it's equal, that equals is a padding out. I forget what the other ones are, maybe underscore or something. I don't see anything in there that's not an alphanumeric character though. Maybe it is just equals and then something else. I thought it was an underscore. In any case, it doesn't really matter. If you were to send something over email, for example, an image is just raw data, 0s and 1s. However, the protocol for sending stuff over email, SMTP, does not handle binary data. So what usually happens is you encode that data as text, and then that's what gets sent over the wire. Ultimately, at the end of the day, everything is a 0 and a 1. But this is a way, and it's no more compact or less or more compact than anything else, but usually it's converted and encoded into some format like this before it gets sent over the wire. And of course then compressed as well. Yeah?
What's the advantage of base64 over working in the format?
It is compact, so it's almost a one-to-one. If you have 64K here, you're going to have 64K there. But it is not binary, null bytes and gobbledygook or whatever. It is these 64 printable characters that are in the basic ASCII text character set. So it get transferred. In fact, we've experienced it already in the grader. Some people are explicitly printing the null byte, and Bash doesn't like that at all. And you'll get some message that says null character, null byte is in the output, and we couldn't display anything, and the test will fail. Not everything can handle. In fact, like if you tried to print the bell or whatever, right? How would it interpret that? It's a non-printable character. All of these are guaranteed to be printable characters. So that's one use case. All right. So again, if you're dealing with these interchange formats, bring in a library. Don't worry about it. Even if you were doing CSV stuff in reality, in a real program, bring in a library. Right? But we are going to look at the basics of input and output. The basics are, 1, you open up the file. 2, you process the file. 3, you close the file. And it's pretty straightforward. This is what you do when you open up a Word file. You double click it, you open it. You type, then you close it, save and close it, right? But if you don't do these steps explicitly in your code, bad things can happen, right? For example, you take for granted with a user interface that a file is there, I can double click it and open it. Great. Right? What if the file's not there? What if the file, you don't have permission for it, right? What if a million things could go wrong with opening a file? Even more stuff could go wrong if you don't close the file. In a Word document, if you close the file, it'll ask you, you've got unsaved changes, do you want to save them or not? Right? And you, oh yeah, I meant to save. Or there's auto-save features or stuff like that. You don't have that with programming. If you have a file and you fail to close it, you could end up with garbage, undefined behavior. It could be that only half the stuff got written to your file if it's output, or you could just have corrupted data, right? So failure to do any one of these steps could lead to undefined behavior in both languages, okay? All right, so let's look at file I/O in C, right? So in C, files are represented with a pointer, that is file star. Now it is all uppercase, so be careful on that. F-I-L-E, all uppercase there, right? To open a file, you use open, right? Just short for file open, right? It takes 2 parameters. First parameter is a string representing the path to path and name of the file. Right? The second is the mode. Second is the mode you want to open it for. Right? R is read. In other words, if we're going to read a file, this is file input. And W, or W. Right? Let me highlight that in both like this. There we go. Let me backtick it and then do that. There we go. R or W. And it is a full string. Even though it's one character, it's a string. It's not single quotes. That's because you can do things like this. You can open it up for reading and writing. We're not going to do that. You can open it up for reading plus appending. Don't do that, right? You can open it up for reading binary. We're not going to do that. So I'm going to keep it simple and only go with R and W. What does W stand for? If R stands for read, write. In other words, file output. Right? It returns, if successful, a pointer, successful, to the file, starting at the first byte or character. We're only really going to deal with plain text files, so those two are synonymous with each other. As you read the file, or write to the file, the pointer is automatically advanced to the next byte, next character, line, etc. It depends on how you read or write the file, okay? I'm going to jump immediately to the end here, and if you open up a file using fopen, How do you think you close a file? For close. There we go. For close. Once closed, that's it. Right. The file is saved. Any attempt to read or write from it after it's closed is undefined behavior. You are done with it. Yeah? No, you can open it, close it, open it, close it, open it, close it as many times as you want. Now, you're also crossing your fingers hoping that some other process didn't come in and open it and close it and open it and close it. Because what happens is you have file locks. So if you ever wondered, okay, I'm going to go ahead and open up a Word document and I'm typing, I'll go ahead and minimize Word. Word is still open the file. It's still working with it. Ever tried to go ahead and delete the file that you're working on? You can't. Try it sometimes. You can't because the operating system will come back and say, that file is in use. There's a lock on that file. So what happens is a process will open up a file. It's got a lock on it. You hope that it has a lock on it. Because if another process comes in and tries to muck with it while there's a lock on it, it'll be blocked, or that program will be killed, or something like that. Because we won't want multiple processes processing the same data. Right? Okay? So let's just go ahead and go over here and show you how it works. All right? So open a file, right, in the same directory. File star F. Sometimes people use H. And that's because FGH. Actually, what the H stands for is a handle, a file handle, because it's handling the file. Don't ask me why. I'll just use F, right? Why not file? Well, easy to get it confused with FILE. Sometimes it's in or input file. I'll just keep it simple and say that it's F, right? I'm going to go ahead and open up this books.csv file, which is in the same current working directory. So open books.csv. And I'll open it up for reading because it already exists. Okay? Later on, I'll close it. For close F. There we go. But I can process it to do process the file here. Right? I want to show you some alternatives. For example, if this file were in a completely different location, file F 2, I'll say, is equal to fopen. I don't know. Let's look at one directory up, and then over in the review. What's in the review file? Review.c. Let's open up that review.c file. There we go. So open a file in a relative path. Right? I'm going up one directory, then down into the review directory, and then I'm opening up the review.c file in that directory. You can also use absolute paths. So open a file in an absolute path. So file F3 is equal to fopen etc password. And I'll open up for reading. All right, there we go. So what's in that etc password file? I think we've looked at it before, haven't we? There are users, there's root, there's X, their redacted password, and then a whole bunch of other information about them. Yeah? Oh, sorry, yes. Read. All right, thank you. All right. So if it fails, and it's not going to fail in this case because I can read it, right? Then it will, well, if it succeeds, it'll return a valid pointer. If it fails, what do you think it returns? A null, right? If it's null, then that opening did not process. Printf could not open file, end the line. And then I'll exit right here if you want to. Right? GCC, oh, I'm in H. So let's make sure that we're in the correct directory. GCC demo.c. Oh, and by the way, I didn't have to bring any new libraries in. Why? Where is all this stuff? In the standard input-output library. There's no file.h or anything. Right. All right, let's go ahead and run it. Well, I could read that file, so everything was just fine. It didn't give me that error message. Let me open up a file that I probably do not have access to, which is the etc shadow file. Let me try to look at the contents of that file. More etc shadow. There we go. Permission denied. What do you think the shadow file is? Remember all those redacted passwords, the X's? That's where the passwords are actually stored. Encrypted, right? Not plain text or anything like that. Actually hash passwords. So I'm not going to be able to open that up. If I try to do that here, F3 will now be null. And I will get that error message printed out. Could not open file. If you open up a file for reading that doesn't exist, right? Blah, 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 right? That probably doesn't exist. Let's go ahead and could not open file because it doesn't exist. You don't have permission for it. You don't have permission to create it, et cetera, right? So you could not open that file. If you open it up for writing and you have permission to create that file, it will create it for you. So no problems there. Let me put this into the notes so that you have it. Remember, all those need to be closed. Since I'm not actually doing anything with it, it's not that big of a deal, but whatever. Right? So to do, process the file. Let's simplify it, and let's only look at the books file, because I know what the contents are. I created it. I do have permissions. Okay? Now what we want to do is we want to read line by line by line. Or actually, you know what? Let's open up something else first. Output.txt. Right? But I'm not going to open it up for reading. Let's do the simple thing first, for writing. Right? Writing a plain text file is super straightforward. If I were to write to the standard output, what would I do? I would use printf, hello, how are you? Right? End the line. There we go. And I'm not printing any variables there, so let me give myself some variables here. Int a is equal to 10, double b is equal to 3.54, because I mashed the keyboard. And let's go ahead and print both of those out. A is equal to %d, b is equal to %f, and I'll end the line on there, those two. So a and b, right? GCC, demo. Actually, yeah, let me go ahead and run this. It doesn't look like it changed anything, but remember, when you create a file, sometimes you have to refresh. And you see that output.txt is there now. Did I actually write anything to that file? No. So when I open it up, it's empty. In fact, if I ls.la output, there we go. There we go. How many bytes is that file? 0. It's just a file that exists, come on, that exists on this system. 0 bytes. So let me go back over here, and instead of printing to the standard output, let's print to the file. Remember that if we were to print to a string, there's a trick we could do, sprintf. Right? Well, if this is a file and not a string, what do we print to? fprintf. And all I do is put an f in front of it, the file handle, the file pointer that you want to point to, that you want to write to. GCC. Run this again. And let's close this and open it back up. There we go. There's my output. Let's try that again and add a couple more things. Yeah, go ahead. Question? To write what? Yeah. You could. In fact, if you want to, we can open up that review.c and change its contents. Right? In fact, I could open up demo.c and write it. In fact, let's do that instead. All right, I'm going to copy this into my clipboard, because what's going to happen here now? Run it. Yeah, it ended up okay, yeah, it ended up what? Overwriting everything. All right, not just the first 2 lines and then closing it. It opened it up and it wiped everything out. Right? So there, I've restored it. Good thing I copied it before I did this. There is no undo. There is no recycle bin or whatever it is on Windows. There is no open up a utility to defrag your hard drive and recover stuff that even has been thrown out of the recycle bin. Right? There is no undo utility, period, when you're doing programming like this. Be careful. Open up the correct file, output.txt. For this reason, a lot of programmers, a lot of developers, a lot of admins will make sure that whatever data is risky is read-only, right? That's a very good thing. Because, for example, I could make it so that my demo.c, I'll go ahead and put a file lock on it or a read lock on it so that you can only read the file, never actually write the file. You do this with GitHub too, or with Git generally. What I do generally is when I commit something to a Git repo that has, say, stored passwords in it, first of all, I take the passwords out, then commit it to the repo. Then on my end, if I'm going to change something and actually put the password there, just to make sure that it never actually gets checked into the repo, I will take it out of the index, meaning that it will never track any changes to that file at all. So that it never, even when I do a commit and push stuff out to a repo, that password is never actually part of it. So be careful. And once you commit a password to the Git repository history, show's over. In fact, there have been plenty of demonstrations that many people just web crawlers go out to all these public GitHub repos, find non-redacted passwords that people have put in throughout their entire history. Oops, I screwed up. I'll go ahead and commit a new change to erase that password, but guess what? It's in your history. So you can go ahead and make a web crawler that goes through the entire history of an entire project looking for passwords, because you probably didn't change it. All right, so that's output. All you need to do is fprintf. That's it. Everything that you know about printf, you now apply it to fprintf. Right? To do file output, just use fprintf. Right. And I'll make sure that you have that in your notes. There you go. Otherwise, it's really simple, okay? What if I wanted to read it, though? Now, there are two ways that I'm going to show you. First of all, there are dozens of ways that you can do this. Many of them are unsafe. I'm going to show you two ways, and both of them are going to be safe. I'm going to read the file character by character, ... All right? So that's going to be fget C, right? File output. Let's do it. Let's do it like this, right? So char C. C is just for current character, or if you want to, current character. There we go. I'll do it that way. Why is it not syntax highlighting anything? Probably because I just cut and pasted. Let's go ahead and open it up again. Aw, darn it. All right. All gloomy red, or all gloomy black and white then, whatever. All right, so I'm going to go ahead and call fgetC on F. So let's parse that out. File, get, you're getting a character from that file. C, what are you getting? A single character, right? So read it character by character, right? I can read the first character. Let's print it out, printf. I read a %C end the line, and current char. We'll do that again and again and again. Fget C, F, current char is equal to, there we go, 1, 2, 3, 4, 5. There we go. GCC that, and let's print out and see what we read. I read HELLO. That's that same output file that we just created, by the way, right? HELLO. If I were to keep going all the way to the end, what do you think I would encounter at the end? Remember that this is a character, not a char star. So it is not a pointer, right? There's something new, right? You'll read, so read until you find the character EOF. EOF, what do you think that stands for? End of file, right? So instead of going character by character by character here, let's write a loop to do it instead. While the current character is not equal to the, and it's this special EOF character. If you look at the ASCII text table, you will not find it, right? Because it's not in there. Technically, I believe that its value is -1. Yeah, it's -1. And there ain't no -1 in the ASCII text table, right? So That's how you know it's a special character. While it's not equal to that current character, I'll say that I read the current character, and then I'll get the next one, the next one, the next one, the next one. There we go. Yeah.
Is that represented by EOF or E0?
EO. Zero always has that slash through it. Right? EOF. End of file. There we go. Let's try it. Try it. There we go. So, hello. Oh, here we go. Hello, how are you? A equals 10, B equals 3.40000. And then there is, what's that last character right there? Oops. What's that last character right there? Hint, it goes to the, not null, but what's that last character right there to go down to the next line that you don't see directly, but you see the effects of it? It's that end line character. Right? So whether or not the last line has an end line character, right, that's technically the last line. It's an empty line. Right? So you could be off by one with files with end line characters. Another common issue is editing stuff on Windows. Windows end line characters are not hyphen or backslash n. They are backslash r, backslash n, or is it nr? I forget. Anyway, in Windows, it's two of these things. And that's not that weird because in the HTTP protocol, that's also the same. Yeah, the problem is always going to be Windows, but there are some protocols that actually use that convention too. What was the difference, by the way? One of these is an end line, and one of these is a carriage return. These are CLRF. CLRF? No. What is it? Clear line CLRF characters. New line. CRLF, right. Carriage return. So it's carriage return line feed. That's what it is. Carriage return line feed. There we go. And I think it's going to be the other way around then. So what is a carriage return? Think about typewriters, right? Because that's what this is based on. Line feed is going to be zip. You go back to the beginning, right? You go back to the beginning of the line. Well, you're still on the same line. The carriage return is going to be rolling that thing to the next line, right? So usually when you get to the end and you do this zip back, it does both at the same time. You're putting it back and then it's also going to the next line, but you don't have to, right? So that's why the difference is there historically, because of old school typewriters. Right? Yeah. No, EOF, that is just a special thing, right? In fact, what is it? It's a macro. Define EOF to be -1 in parentheses, because otherwise then it's interpreted as math, right? Okay. There's character by character, I should say. Right? You can also, as an alternative, read the file line by line instead. Right? To do that, I'm going to use a very similar function, but instead of fgetC, I'm going to be file get, not line, but string. It's going to get an entire string. fgetS reads on up to on entire line and places the results into a buffer string. Right? The string's got to be large enough to hold any line. So if you've got files with really, really large lines, that's terrible. Like if you've got one file that holds a bunch of DNA strings and it's all on one line because they thought, to hell with carriage returns, to hell with line breaks or whatever, right? Not great, because now you have to predict how long this line will be. For most of our purposes, though, we'll tell you maximum line length is going to be like 1,000 bytes. So we need a buffer to read that into. Buffer, and I'll just make it 1,000. Right? We can read any line that has up to 999 characters. Why did I just say 999 instead of 1,000? Null terminating character. Right. It's going to put the null terminating character in there for you. Begets automatically adds the null terminator for you. Dot, dot, dot. All right, so let me show you how to use it. Begets buffer. Into buffer, right? Yep. Then the size, 1,000, and then the stream, f. There we go. So let's read that together. The first argument is the buffer. That's the string that the contents are placed into of the line, right? 1,000, that's going to be the maximum number of characters or bytes to read -1. Again, why -1? Because it handles the null terminating character for you. So this number needs to match your buffer size. Why do I keep calling this a buffer? What is a buffer? Well, in this case, a buffer is I'm treating it as a file. It's just a spot of memory that you can put data into and then read data out of. I'm going to read the data, process the data, then I'm going to read the next string that gets pushed out, right? It's just like a video when it's buffering. It loads some data in here so that you don't have to, sit there and spin. It loads like maybe the next 5 seconds or something, so you're always 5 seconds ahead. And then, of course, they don't want to give you the entire video all in one go, and that's why you bring in a plug-in to do it for you that loads up the entire video, or just YouTube downloader. Yeah.
Is there a reason why we're using a static string?
You don't have to, but that's because I don't want to have to clean it up afterwards, right? Any line is going to be small enough that you're not going to reach an issue with stack space. If you're reading one of those DNA files that's 1,000,000 characters long on one line, right? Then yeah, you're going to have to do something else. All right, so the last argument, of course, is f is the file pointer handle that you want to read from, just like f was up here. Okay? Let's print that. Printf. Line is equal to %s and the line, and buffer. Let's do that over and over. Once, twice. There we go. Hello, how are you? Then line is equal to a is equal to 10, 3.4, blah, 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 blah. Right? Why were there extra spaces there? There are no extra spaces here. Where are the extra spaces coming from? There are spaces in the line, in the file itself, or end line characters, sorry. End line characters in the line itself, but also, what else am I printing here? End line. It's common that you don't want those end line characters in there. If you don't want those end line characters in there, what could you do? There's an operation called chomp out the end line character. Right? So if that last character is going to be an end line character, I want to make sure to get rid of it. How do I know where the last character is? Question mark, question mark. If that's equal to the end line character, I will go ahead and chomp it out. Buffer of whatever that is equal to the null terminator character. There we go. All I'm doing is taking that end line character and making it into a null terminating character, effectively taking it out. Right? So what is that last one right there? No? HELLO, end line character. How many bytes is that? How many characters is that? 6, right? So this is 0, 1, 2, 3, 4, 5. So strlen gives me the length of the buffer -1. There we go. Do that again for the second one, and we've effectively taken out those end line characters and then restored them only when we actually print it. Right? So this is called chomp, right? Or some languages call it trim, right? They have a trim function for you to do this that trims out leading white space, trailing white space. Ltrim, rtrim are other functions. Trim out leading white space, trim out justified white space, right? So L trim, R trim, trim, chomp is what I call it. Why? Because I learned that in Perl. And Perl has this chomp function. What happens if I do this one more time? Is there another line to read? Kind of. Let's find out. There was not another line to read. It just repeated the last line. Why? So when you get to the end of the file with fgetC, you know that by checking EOF. You don't have that with fgetS because it's returning an entire buffer, an entire string. Right? So it returns, when it reaches the end of the file, it returns a null pointer. So that's something that we actually have to capture. Char, I don't know, call it, I've already got F. What should I call this? I'll just call it file pointer. Right, there we go. And always make sure to capture that value. FP is equal to that. There we go. FP is equal to that. Oops. And at the end, let's go ahead and look at what it looks like. Printf, FP is now percent, well, it's a pointer, so I'll go ahead and go with percent %P, end the line, and FP. Nil. That's because it's a null pointer. My, lots of repeated code, lots of repeated code, lots of repeated code. Let's rewrite this as a while loop. Right? So I'm going to keep that char. Actually, I'm going to keep this entire thing here. Right? And I'm going to put this into a while loop instead. While fp is not equal to null, right? All caps NULL there, I will go ahead and process that line that I just read, and then set myself up. Actually, what I'll do is I'll maybe, yeah, chomp it out, then process it. I don't like that. Let's chomp it out up here. 1, 2, 1, 2, 1, 2. Then print it, and then read the next line. There we go. And get rid of this stuff. And make sure to close it at the end. So again, what I'm doing is I'm reading the first line. That sets me up for my while loop. While that pointer, that fp, is not equal to null, I'm going to chomp out whatever's in the buffer, print it, and then I'm going to read the next line. When it comes back up here and you have no more lines to read, it returns null, and that's it. You break out of this loop. GCC. And so I should have exactly however many lines are there. If I change this to open my CSV file, books.csv, there we go. Actually, intentionally misspell it for a second here. What do you think is going to happen? Segmentation fault. What should I have done? I should have checked to see if this returns null to begin with. CSV, let's correct that. Oops. GCC, run it. There we go. So the first line in this case was 20, then Harry Potter at the beginning, and all the way down here, A Game of Thrones. Right? And is that the last one? Books CSV. Looks like it to me. What if I had blank line, blank line, blank line, blank line, and then garbage? Save that. I don't even have to recompile because I just made changes to the file. What's it going to do? Blank line, blank line, blank line, blank line, garbage. Right? What if it's not garbage? What if it's just a space and it looks like a blank line? Same thing. Right? So how do you know that you're reading valid data, or these are just a bunch of blank lines that somebody mashed their keyboard in at the end? Right? That's why generally when I give a CSV file, I put that thing at the top. Read the next 20 lines, not the next 29 lines. Right? Only we give you hints like that, or we give you help like that. And the most common error is to ignore one of those things. If you don't know how many lines there are, you can count. How would you go about doing that? So, compute the number of lines, .. int num lines. is equal to, well, you start out at 0. And processing it now doesn't mean printing it. Processing it now means counting it. Numlines plus plus. After you're done, closing it, printf, I read %d lines, numlines. CCC. 28 lines. Are there 28 lines in there? Oops, books. Yep. Remember, line 28 was the one with that space on it. Right. You could do the same trick with characters. Count the actual number of characters are in it. Because if you need to, for example, in your hack this week, if you need to determine how big a file is, one way of doing it is open it up. Count the number of characters. Count the number of lines. Close it. Open it up again. And process it again. I will mention that there are a couple of other things that you can use. There's seek in C, and hopefully it brings up everything else. Seek. So you can basically you can fast forward, you can rewind. That's probably actually what you want. C file IO rewind. There you go. And the other one is what is it? You jump to the end. I forget what it is. Rewind. Well, maybe rewind will tell us, or C also. As fseek. That is, this is just one. Rewind means that you're going back to the beginning, all the way to the beginning. It's equivalent to fseek, and then going back to the 0th byte. Is it fast forward? I thought there was a fast forward. I forget what it is though. Yeah, exactly. That's the point that I was going to make. Why do we call it rewind? Why do we call it seek? Why do we call it fast forward? Think back to like some old-timey movies where you've seen computers. What are they? These big giant mainframes with what on them? These tapes. These big giant tapes where you needed some data on that tape. So what did you do? You fast forward it or you rewound it, right? When all data was stored on tapes, this is the nomenclature at the time, right? And it kind of makes sense because, you know, if you are treating this like a pointer and you start out at the very beginning and then you read character, then the next character, then the next character, then the next character, well, you can also go backwards, right? Go back a character, go back a character, go back a character. Where this highlight here is always a tape head. It's always looking at one particular character, and it could go backwards and forwards just as easily. Right? So that nomenclature still works if you think of it in terms of pointers. Okay? All right. We don't have time to do it, but we will look at file IO in Java. It is just as it's easy. In fact, it's even easier because all you need to do for file output, you just need a buffered, buffered output file stream, and then system.out.printf, system.out.println, system.out.print. What do you think out is? It's a file, right? So all you need to do is create your own file, and now you can use printf, you can use println, you can use print. Right? That's file output. How do you do file input? It's really easy. In fact, there's a library that I'll also show you at the end called the non-blocking Java I/O library that allows you to just read an entire file in at once, or read all the lines in at once. Right? We'll take a look at that on Wednesday, though. Any questions on the C version? Always remember, close, close, close. Failure to close may mean that you have corruption. I don't think it'll corrupt it in this case. Hopefully it didn't, because I didn't cut and paste it. That's not what I wanted. Books. There we go. Nope, it didn't corrupt this file, but it could have. 99 times out of 100, it won't do anything bad. It's that one time out of 100 that it does something bad, and now you've lost all of your data. And there's no undo. There's no backups unless you've made backups. All right. Then I'll see you on Wednesday.